Hello, so my name's Lois Gray from North Island College, and today I'm going to show you how to use your test vectors that we programmed or that were in the example of the Brakelite flashing system that we looked at when we were looking at our ABEL file for programmable logic devices. So we start by opening the lattice semiconductor ispLEVER IDE, which you saw last time. Lattice Semiconductor ispLEVER Classic Project Navigator. And we're going to open the Brakelite example again. So if you'll remember from last time, if you go under File, Open Example, these examples are downloaded when you download the IDE and obtain the license. It's a simple programmable logic device, SPLD, and it's a gate array logic device as well, so it's under this GAL file, and the one we're interested in is the Brakelite example. The .syn suggests it's a complete project that's synthesizable. Okay, let's make this a bit bigger so you can see a bit better what's going on. So you'll remember that the last time we looked at the .abel file, which was our text file, which was then compiled and ran to generate the fuse map to actually program a real hardware device to do the program that we'd written in the .abel file. This week we're going to look at the control vectors instead of the ABEL file, and as you remember, the options you get on the right hand side here are dependent on what you select on the left hand side here. So if we select control vectors, I've already probably done this, so that's why our compile test vectors is ticked. It doesn't matter whether that's ticked or not. We're going to do a functional simulation. We can't actually do a timing simulation because we haven't got a real device to test against. But we can do functional simulation to see whether the program responds to the inputs the way we'd expect to. And if you remember, the Brakelite is a state machine which basically runs through state 0, I think, to about state 6 or 7, and then resets, depending on whether a right break indicator is triggered or a left break indicator is triggered, but we'll see that when we run it. So if we click on functional simulation, if we double click on that, we would expect this to run because it's an example. If you have written your own test vectors, you may get an error down here and you would get a big red cross here saying why it hadn't run, or sorry, get a red cross there and then an explanation of why it hadn't compiled down here, which you can then click on and correct. It is also possible to write separate control vectors. At the moment, if I double click on control vectors, you'll see here that we actually just see the ABEL program. And that's because the vectors were part of the main text program. They can be written as separate text vectors, but for a small program like this, there's no reason not to just include them all in one file. Just keeps everything together nicely. Okay, anyway, so we'll do the functional simulation. What we get is a simulator coming up, simulator control panel. Control is the name of the program, or the top level project that we are simulating. And you should get loading netlist successfully, means that it's ready to run. So we can run it with this exclamation button here, or we can also use these top line commands. Simulate, run does the same thing. You'll see that there's a resolution step of 100 nanoseconds, so we're going to take measurements every 100 nanoseconds with the simulator, and we're going to run for a total of time of 15,400 nanoseconds. So these are both editable. There will be a minimum resolution that the system can cope with, and obviously there will be a maximum runtime as well. So without further ado, let's just simulate this. So if we click the run button, we wouldn't expect any errors, we don't get any errors, and the system runs a simulation. It's just a functional simulation, so these times are not exact. They're steps of 100 nanoseconds, so they're to the nearest 100 nanosecond, but the actual real device will have delays which are not necessarily shown here on this diagram. So if we click this edit button here, and just click it again, what we get is a variable cursor which we can move around on the screen here, and we can click it there on the window, on the waveform, and we can get some information about this particular point in time for the functional simulation, and down here it will tell us that at 2,900 nanoseconds, this clock signal is high, and a strong high, whereas, yeah, that's also high. Let's find a low one. This one is low, so RB0 is low. Okay, on the left here, if I just click Edit again, on the left here we have a list of all the signals that are being seen in the waveform viewer. So you'll recognize these hopefully as your inputs: clock, output enable, right break indicator, left break indicator. And the rest of them are your outputs or state assignment bits: left break 0, 1, 2 and 3, and right break 0, 1, 2 and 3. You'll see the one that's actually being measured is kind of slightly highlighted. So that's the one that's the information down here is telling us about. The other thing we can do is we can add additional waveforms if we wanted to. We actually have all of them here, but if we click on this button here, all the possible choices of waveforms appear in the right here, and we can just add them by clicking on them and then clicking Show. Equally, we can remove a waveform, so RB0 is selected at the moment, so we can remove that by clicking here, and we can no longer see RB0. If we want to bring it back, we want to show RB0, so let's click on that, just go for a show. If you have buses, you can show buses as well, but we're not looking at buses this time. If we want to rearrange the order, you just left click, hold and drag the signal to where you want it. Oops, that didn't work. There we go. One other thing we can do, well, a few other things. You can zoom in. Obviously these buttons here are your zoom buttons, so say we wanted to measure the delay between the left break indicator going high and the state change of bit left break 0. We could zoom in on that, and we could measure it manually. So, oops. Oh, why is that not letting me do that? It's not letting me come out of that, so I think we'll go back onto query. Yeah, so we can measure it manually between, where did it go? I think I zoomed in too far, didn't I? Let's zoom out again. Yeah. Okay, I think we need to do the query to come out of the zoom window, the zoom command. So if you just click on this little head query thing, we've then got the option of querying the waveform again. So we can put our query button down there. We could manually measure that that was at 3,100 nanoseconds and then move the query line to where we start getting output. This time at 3,200, and we can subtract those. Or alternatively, you can also put a marker on. There's two options with this button here or on the top line here under Object. Just use the button here. We can place a marker there, and then down here we will get a measurement of the difference between the marker and our query cursor. So there's 95 nanoseconds in this case between the right break indicator going low and the right break state machine reacting to that. Of course this would be a setup time prior to a clock, because you can see that the state bits react to the same thing as the clock edge, and you can quite clearly see there's no delay, so that shows you that that's not timing simulation, that it's only a functional simulation. In real life there'd be some delay between this clock edge going high and this output going high. But obviously you can see here you have to not contravene the setup time of the device, so the time between you changing an input and the clock appearing. So you could actually measure the setup time that you've allowed, which in this case is plenty. It's 100 nanoseconds, 95 nanoseconds. Okay, the only other thing that might be of interest is actually checking that the signals are doing what we expect. So we can full fit the waveform back to the screen again by doing that. Just go back to our query button so we can move things around. I think I'll remove the marker as well. Just click on that to remove the marker. And we can move the query button around, but we can see if things are happening as we would expect. So first of all, for this first few seconds we actually have the output enable high. So we would expect the outputs to be in a high impedance state while that output enable's high. If you remember, the output enable was active low, so high is the inactive state. So if we do a query there, it didn't quite go into the right place. I think I might zoom in a wee bit just to let you see that a bit more clearly. We do a query there. It should, if we look at one of the, it tells us that that's in a high impedance state, which is one of our outputs, RB3, that we're looking at. We could look at LB0. That tells us the same thing. And that's because the output enable's high. Okay, back to full screen again. The first thing that happens is our right brake indicator is going high, and we should step through the states of our state machine. So you can check that with the state bits. First of all, we've got condition where it's 1, 1, 1, 0. Then it goes 1, 1, 0, 0. Then 1, 0, 0, and then all zeros. And then it stays in that condition until our indicator goes off again, which is this low edge here. And then on the next clock edge, we start clocking through the rest of the states to get back to state 0. So again, we're going 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, and 1, 1, 1, 1. And you can see the same for the left brake indicator. And at this point, we've got both the right and the left occurring together. And we can see our state machine for both individual state machines, rather, one for the left and one for the right brake, clocking through the same. So hopefully that will tie in with the diagrams that you have and with what you looked at when we looked at the ABEL file last week. That's really all there is to it. If this doesn't work, it's because you haven't written your test vectors correctly. This is not showing us, it's not got any intelligence as such. All it's doing is using the test vectors to create a waveform diagram that you can look at and observe. Okay, that's all for now then. Thanks for listening. Bye then.